Hello, my name is Manuel Duclos-Vergara. I am originally from Chile, but I've been living in Norway the past 13 years. I currently work for Schibsted, processing tracking events using technologies such as Kafka, Kafka Streams, and Spark. In my presentation, I will be talking about the design and architecture of systems using Kafka and Kafka Streams. I hope you enjoy. Hello, my name is Manuel Duclos-Vergara, and I'm going to be talking about processing billions of events using Kafka and Kafka Streams. About me, I'm originally from Chile. I have lived in Belgium and in the US because of my work, and I've been living in Norway since 2007. Currently, I work for a big company called Schibsted. Schibsted, it's an international family of digital consumer brands with more than 5,000 employees. We have world-class media houses in Scandinavia. We have leading marketplaces and digital services that empower consumers. Millions of people interact with Schibsted companies every day. So, what are the goals with this presentation? I have set 3 goals from my side. The first one is to present that streaming is not only about speed. There is way more to streaming than just the speed. The second is there is more to streaming than just the streaming part. There are a lot of other things that you have to consider when streaming. And finally, I want to convince you that Kafka is a great streaming platform and you should use it in your projects. So with that being said, let's look at the basics. We will look at the scale of the problem. You remember I said processing billions of events. We will look at what is Kafka and how it works. And we will finish the basics by looking at what stream processing is actually. So the scale of the problem, what is it? What does it mean to have 1 billion of events a day? And this is an average. Sometimes you will have more, sometimes you will have less. So if we start by the physical constant, 1 day is 86,400,000 milliseconds. That's unchangeable. And 1 billion is still 1,000 millions using the short scale. So even if we were processing each event in a millisecond, we will still be short by an order of magnitude. To put it another way, we need to process around 10 events per millisecond to be able to keep up with the demand. What is Kafka? Well, Kafka is a distributed log system of immutable records. By this, it means that the system is distributed among several machines, although it is technically possible to run everything in one machine. And by immutable, it means that once an entry is written to the log, the content cannot be altered afterwards. Basically, once a record is written to the log, you cannot change it. And what is a log in Kafka? Well, a log, it's in Kafka terms, it's called a topic. And each topic is divided into partitions for performance reasons. And in addition, each partition can be replicated for reliability. Here you see that I have this topic and I have several partitions. And then I zoom into this partition and I see that each partition has replicas. And these replicas are just copies of the partition with all the records. What differentiates Kafka from other systems is that records are not consumed. What does it mean? When you have a queue, for example, you consume the record because you pop it or you dequeue it from the queue. In Kafka, you don't do that. In Kafka, you basically read a record and advance the read pointer. Once you have advanced the read pointer, you're reading the next record. But the record is still there. If you want to go back, you can just move the pointer back and read the previous record. The reading process is per partition. So basically, a consumer can start reading a partition and advance on the records over that partition. You can have several consumers, and they won't interfere with each other. Each one will have its own read record. The parallelization in Kafka can be done in several ways, but the basic unit is the partition, as I was saying. So if a topic needs to be consumed by several processes, you can have several partitions, and as many partitions as processes you need. And Kafka provides a very interesting abstraction over this consuming part, and that it's called the consumer group. What is a consumer group? A consumer group is a bunch of consumers, it's a group of consumers that work together. They all operate under the same ID. So they look the same to the processor, to the Kafka cluster, and they all distribute the partitions, the available partitions. So each consumer is processing one partition. In this example here, we see that the green group has 4 consumers. And we see that there are 3 consumers that have one partition each. And there is another consumer, the one that is marked inactive, that didn't get assigned a partition because there are only 3 partitions. So that consumer will be inactive. Now, the good thing about this is that if one of the other consumers fails, this inactive consumer will be ready to take over and could replace the consumer that failed. If we look at the other group, the pink group, we will see that one consumer got assigned one partition and the other consumer got assigned 2 partitions because there are only 2 consumers. So one of them had to take 2 partitions. A note about the partitions. It sounds very tempting to have topics with a lot of partitions, but the number of partitions has to be considered very carefully because there are other costs when partitioning a topic. It's easier to start with a topic with a small number of partitions and then scale that one than to start with a topic with a large number of partitions and then try to shrink it. That's very difficult. Now, what happens when we produce records? How does that work? Well, we have producers, and each producer will store records. Now, the production of records and the writing of records is done by partitions too. How do records get assigned to partitions? Well, there is an algorithm, and that algorithm works by assigning records based on the key. So it will basically assign records with different keys to different partitions, and if a record has the same key, it will be assigned to the same partition. And this brings the other problem. We have to be also very careful when assigning keys, because otherwise we will have partitions that are not distributed evenly, and we might have a partition that has too many records and partitions that have very few records, in which case the parallelization will not work that well. If you have that situation and you need to assign records using a different schema, you can do that. Kafka allows you to specify your own partition assignment because the partition assignment is done by the producer itself. The producer will decide to which partition a record is written. So you can assign the default algorithm that you want to use to do that. Now, if you remember the title of my presentation, I mentioned something about Kafka Streams. What is Kafka Streams, actually? Well, the name, it's a little bit misleading because one is used to talk about streaming and Kafka, and Kafka Streams sounds like the same thing, but it's a completely different thing. Kafka Streams is a processing library. It's a processing framework that it's based on Kafka. It is designed to process data in Kafka. It provides stateful and stateless transformations. It provides also a very advanced query system that it's called KSQL, and several abstractions that you can use to operate on streaming data. Of course, Kafka Streams is not the only framework you can use to process your data. You have, for example, Apache Flink and Spark Structured Streaming and other frameworks that you can use. But Kafka Streams is developed by the same company and the same open source team that develops Kafka. So it's very well supported. Now, let's jump to what is stream processing. Now that we have seen the scale of the problem, we have seen what is Kafka. What is a stream processing? Well, a stream is a sequence of data packets over a time interval. Mathematically, a sequence of tuples over an interval, as I wrote there. But let's put this into a picture, because a picture is worth 1,000 words. Streaming is like a conveyor belt. You have packets in the belt that are transported, and it's a continuous flow. But what it's special about streaming is that you're not concerned about the flow. Each packet is processed individually. So you see there is a machine in the middle, and that machine will do something, but that machine does it for each packet and each packet that comes afterwards. That's the key of stream processing. As I mentioned before, streaming is not only about the speed, because many people think that you use streaming when you really need performance, when all that matters is to get those extra milliseconds out of the way. And this is supported by the fact that with streaming, you're processing records as they arrive, as I show in the picture. While, for example, in batch processing, you wait until you have a batch and then process those records. Well, in truth, streaming is about changing the state of a system by small amounts. I try to make this as clearly as possible. You see that in the streaming side, we apply small deltas and we change the state. So you see that we have an event 0, that applies a small delta and rotates the element a little bit. And then we have event 1 that applies yet another small delta and rotates the element again. While in a batch processing, we apply a big delta, and we move. And this happens over time. Why does this happen like that? Well, because in batch, you wait until you have a batch, and then you have to apply a very big transformation. While with stream, you're about changing those little events that happen in between, you're applying those as they happen. Now that we have discussed the basics of streaming in Kafka, let's look at the considerations, what you should look when you're building streaming systems. We will change the terminology here a little bit, and we will use records and not events, because not everybody's going to be processing events, but everybody could say that will process records. And it's because it makes it simpler for some of the concepts we will use. So the first thing is that not all records are equal. Why do I mean by this? Well, some records require fast delivery. Some other records require very complex processing. There might be very big records that cannot be directly transferred using streaming technologies. and might require a hybrid approach. And you name it. We all know that all systems have their own peculiarities. So the first thing that I encourage you to do is to separate the records by their classes. The names that I'm using here are purely referential, and you can use the names that you want when you're designing your systems. The important thing is the separation, because in any streaming system, you will have different kinds of records. And I put the signals on top because usually the signals are the faster moving records through a streaming system. You have processed data, basically data that a record that gets into the system needs to be processed and then moves on. And then you have enriched data. Enriched data is data that needs to be joined with some other data that might be part of the streaming system or might be an external system. Think about, you have records that have with a GPS location, but you want to change the GPS location to, for example, the country name. Then you need to take that record, locate the country name based on the GPS coordinates, and put that into the system. For example, if you were considering, do I need to take care about GDPR or not, for example, then you consider, is this within the GDPR zone? Yes, no. For that, you need to enrich this. You get the GPS, you check it with your database. Sure, you need to. Then you put the GDPR flag on. Another thing that usually gets forgotten by people when designing a streaming system is that a streaming system is live. It changes over time and it's dynamic. But you will be requested the first day, I need this kind of data delivered to this database, and the next day will people say like, okay, we don't need that data now, we need this other data, and we don't need to write it to this database, but we need to write it to this, I don't know, S3 or this other blob storage or whatever. So whenever you're designing a streaming system, you need to consider the dynamic configuration of the system from the start, because you will need a way to change the processing that you perform to records and the delivery, where you deliver the records. And of course, the intake, where do you get your records from? And then we have the problems. How do we change this configuration? How do we allow changes without breaking it? Well, we need a way to specify what kind of data they want, how they want us to process it, and where do they want it delivered. In some cases, a web portal is the solution. If you have a system where you control all the inputs, all the outputs, and all the types of processing. Sometimes you need something more powerful, like configuration files. You have power users that can specify their transformation using some kind of JSON query language or XML query language or whatever query language that you want, or transformation language. So you allow them to write those files, and then you apply them on top of things. There might be some other ways that you have already in your company or you might consider. The important thing is you need to evaluate. A web portal, very simple, doesn't require that much training. Most people will get it very quickly. Configuration files, it's complicated. You require power users. You require people that understand the language that it's used to describe those records. And more importantly, you need a way to validate those configuration files before they are put into production, because you don't want those configuration files to break your platform. And that brings me to the next point. You need isolated components. This is common knowledge, but I just wanted to highlight it. If you have a system with tightly coupled components, then if any of those components fails, then your whole system is going to stop and you might not be able to recover it. While if you lose that coupling and one of them fails, you might still be able to run your system. You might still be able to fix it and keep it running at half machine while you really fix the problem. So in this case, for example, if you have the configuration and you have the publishing of the records and all that, you might want to isolate the processing from the configuration changes and the delivery of records. You might want, for example, that the delivery of records does not respond directly to configuration changes, and you might not want the processing of the records to respond immediately to a configuration change. You might want to run some tests over the configuration. You might want to put a message, for example, to a topic in Kafka, say like, okay, now it's time for you to read the new configuration. Now we're done, and so forth. The key thing here is that you need to plan for graceful failures and service degradation. A very important topic these days is privacy. And how do we make sure we protect the privacy of our users? A platform that is built with privacy in mind, it's easier to design and maintain than one that needs to incorporate the privacy after the fact. As many people discover when suddenly GDPR came to the picture. If you start designing things with privacy in mind, it will be easier for you. For example, the things that you need to keep in mind: what type of data will be collected and stored, how long it will be stored, how it will be stored and where, and who has access to the data under which circumstances. Those are questions that it's better to have clear before you start designing the system than just after the fact. And I mentioned it shortly here, but GDPR. This is something that, as long as you have European customers within the European Economic Area, you will have to consider. How do we handle the user preferences? What about the takeout, the portability, or the deletion, the right to be forgotten? What about the data retention? People think that because it's a streaming system, you don't have to worry about data retention. But that's only the beginning, because you have the streaming system that might have very short retention times, but you're then storing things into S3 or a database or somewhere else. And those things also need to be considered. How are you going to be able to say like, okay, sure, we process this and it's out, it's not in Kafka anymore, but this database there still has it. Do you have a data catalog? How do you control that? It's very important that you consider that from the very beginning. Another very important thing is capacity. And this is always important to take into consideration, even now when everybody's talking about cloud and hardware as a service. Because capacity is way more than just computers or terabytes of storage. It is also about how does the platform should behave when the load changes. How do we scale the platform? Do we need to scale the platform? Is it acceptable, for example, that we say, okay, sorry, we have reached the maximum amount of events we cannot process? I'll send some kind of 429 request if we were using REST and tell people come back later? Or do we need to be able to scale? And if so, how do we scale? Do we scale vertically, horizontally? What is the time frame that we need to scale? In our job in Schibsted, we have systems that are very varying for example, we have newspapers, and every time there is a big news, there will be a peak. So we have to be able to scale our system very quickly because everybody will be clicking and liking and sharing and reading news. While there are places like a marketplace where, yes, sure, there will be times when people connect to a marketplace and do that, but the scaling for a marketplace is very different because you can't say to people, yes, we're scaling, please come back in 2 minutes or so. While if you have a newspaper, it's very difficult for people. What if you have, for example, a finance operation? Will it be acceptable for customers to be told, sorry, our platform has already reached the number of users, come back later? Maybe, maybe not. So that is something that needs to be considered. With all this in mind, let's talk about reliability. What kind of service level do we offer? We need to set the target and build a platform around that. How do we handle blackouts? It's very important to have thought about it because people tend to think like, oh, well, we're in the cloud. We can always do something. Yeah, but what is that something? How are you going to detect that you have a blackout? Not that long ago, probably a year and a half, there was a big problem with the DNS service in Amazon, or was it in Azure? And people suddenly lost control over a big part of their systems. So what's your plan for doing that? Is it okay to say like, okay, there is a blackout, there is nothing I can do? Do you need to build something thinking about several data centers in the cloud, several providers? How many nines are you going to support? And finally, you always have to think about when things go bad, because they will. There will be issues. Either you plan for them or not, there will be issues. So you have to plan what to do when things go. One thing that you need to think of is, do you go for data loss or do you go for data duplication? These are the two extremes. If you go for data loss, you mean that, okay, we might have received some requests before the problems arrived, but we lost them because there was this major crisis that we didn't have any control over it. And sorry, customers, we lost those. On the other hand, you have data duplication, which means you have built your system so you will process each record at least once, which means that you might process a record twice if there are major problems. You go back in time and you start processing again. How you need to be clear on those things. You need to be clear with your users. You need to be clear in the platform how you build it, and you need to try to mitigate as much as possible either side of the equation. Neither data loss is a good option as such, or data duplication is so you need to plan, okay, we will minimize the data loss to the last 2 minutes, to the last minute, which might be a lot of data, but, well, it's very limited. Or we might say, like, okay, we will have duplication of data for the past minute or past 2 minutes. Again, it might be a lot of data. So plan accordingly. So with all the things that I have talked now, we have gone through the basics and we have gone through the considerations before building a streaming system. Let's look at the architecture of a streaming system. if we look at a canonical streaming system, there will be three main components in a streaming pipeline. From left to right here, you have the ingestion. Basically, at some point, records will come into the platform. Then there will be a processing component or processing components, depending, where basically records are processed. They are taken from the ingestion pipeline, subject to some transformation, and then put on the other side. And then there will be a delivery of records. Since we're talking about Kafka, I took the liberty of drawing Kafka as the backend for all this. Notice that I draw only one Kafka cluster here, but you could have several clusters. That is just to illustrate the point that we are talking about Kafka. So let's talk about the ingestion. How will the platform ingest records? What kind of records will it handle? Do we need to account for large payloads? Do we need to account for late arrivals? What about arrival patterns? So those are three questions that are very common, or four questions, sorry. What kind of records will it handle? Are there binary blobs? Are there JSON, some kind of JSON? Are there XML? Are there any other format that we may have? What can we learn about that? Do we need to account for large payloads? I know what is a large payload to begin with. If we're based on Kafka, Kafka operates well under records that are under 1 megabyte. Up to 1 megabyte, it operates very well. Over 1 megabyte if a record is over 1 megabyte, then Kafka starts to have problems. So if we're consuming records that are more than 1 megabyte, how do we handle those? Typical situation is that you put the record into a temporary storage like S3, and then put a message in Kafka with the location of the record. Do we need to account for late arrivals? What is a late arrival? Basically, if you're processing things based on date and timestamp, and you are, for example, processing 10:30 now, what happens if you receive an event that it's timestamped at 10:15? Do we need to account for that? And do we need to reorganize the data? Or can we just ignore it and drop it because it's out of order? What about the arrival patterns? For example, a very typical arrival pattern for a newspaper is that you get a peak in the load from around 7 o'clock in the morning to 9 o'clock, when people actually leave their houses or wake up, read the newspapers while having breakfast, going to their work. And then there is a flat curve the rest of the day until the time people start leaving their houses around 3, 4 o'clock in the afternoon. And they leave their works and they go either to meet somebody or go back home and that kind of things. And then there is a new peak. Is there such a pattern for you in your case? The usual solution for ingestion is having a RESTful API. And you can have either a purely Kafka solution, or as I mentioned before, you can have a Kafka with an object storage like S3. But REST, usually it's a very good alternative for ingestion. They are very easy to build and operate. They have an acceptable performance. In our case, we have a REST API and we have no problems consuming 1 billion of events a day. And we even can consume 2 or 3 times as many events without many problems. What you do is basically you have one or several REST endpoints, and then you save the records to Kafka. As I said, if it's too large, you just put a pointer and store the payload in S3 or any other object there. Now, let's look at the processing, because consuming events is one thing, but it's nothing without processing. What kind of processing do we offer? How do we perform it? Does our processing generate signals that are consumed by other systems? For example, a typical example is a build, or you commit something to GitHub and GitHub sends a webhook to, I don't know, Travis or any other build system. And that signal has to be processed. Do we have such situations in our system? Do we have something that generates a report and that report needs to be delivered, or an email needs to be sent to somebody? We have two types of pipelines. We have the fixed processing pipeline. Basically, this is the simplest model. You have a record selector, a filter, and a transformer. It's very simple to implement and test. In this pipeline, you can replace each one of these operations with the identity, basically making the operation a null operation. So you select the records you want to process, the type of record, then you filter them based on properties, and then you transform them. Or you can have a dynamic processing pipeline, in which case you have operations that create chains, and you have each pipeline might be unique. They chain operations, and the output depends well in the configuration that you have. This is more complex to implement, and it's more complex to test. But there are several benefits to this design. Enrichments can be performed in the middle of the pipeline, and not only before or after the pipeline, as in the case of the fixed pipeline, because you already have a set of operations, and if you want to enrich something, you cannot do it. You either put it before or you put it after. While with the dynamic processing pipeline, you create the pipeline as you want. Or you can have a hybrid pipeline, incorporating elements of both. Now, let's talk about the delivery of events. How are you going to deliver events? Do you have a push-based delivery? You have a dispatcher that sends the events to somebody? Or do you have a pull-based delivery, in which case the consumers themselves are responsible for fetching the records from Kafka? Both solutions have their pros and cons. If you have push-based delivery, then you have to implement the logic and the support for the backends. If you have pull-based delivery, where the consumers fetch the records, it's their responsibility and they scale it and they'll do that. But then you have to grant them access to either your Kafka cluster or to something that provides them with access to the records. And of course, the setup of both. Where do we specify that? How do we handle that? And that's all I have to say. One final word. We are hiring. So if you have any, if this sounds interesting, this is what I do every day, more or less. If this sounds interesting, look at that URL there or drop me a comment. And with that, I thank you for your time, and I'm ready to answer any questions you might have. Okay, I have two questions here. The first question is, what are the main problems, technical or architecture, you face while using and maintaining Kafka clusters? Well, this is a large question. Using the Kafka cluster, the usual problem is, how big do I need? How big is the Kafka cluster? And this requires careful consideration, because do I need one very large Kafka cluster? Do I need several medium-sized Kafka clusters? Do I need a lot of small Kafka clusters? And there is no answer that fits all. In our case, for example, we are using a relatively large Kafka cluster because it's easier for us. And by relatively large, I'm talking about 30 brokers. But our consumers have their own Kafka clusters downstream. Basically, we don't need to scale that much. But we have considered several times whether to split this cluster into two. About the maintenance of Kafka clusters, well, there are several sides of maintaining. The usual ones are, well, how do you keep up with the latest software versions? How do you upgrade the cluster? At some point, we have this rolling update strategy. Basically, you replace one broker at a time. But in order to avoid all those problems, we decided to stop hosting the cluster ourselves, and we found a provider on the internet. And this provider has simplified our life quite a lot. They take most of these tasks, coordinate with us, and help us. So, yeah. Depending on your situation, you might want to do it yourself. Things to consider: how big or how many clusters, and how to upgrade the software and plan the capacity. The next question is, how do you manage long-running tasks that can be further split into smaller tasks? How do you manage all timeouts and keep alive embedded into Kafka Streams? Yeah. In our case, for example, we have long-running tasks, very many long-running tasks, because we are constantly consuming. And the way it works, it depends where the problem is, but we try to put the management of the timeout. For example, if we are doing enrichments, which can take a long time, basically we have a record, we have to query some other system outside. This record we will, for example, if it's a REST system, it might take several seconds, or it might take even minutes if there is an overload somewhere. So we try to avoid this by using the Kafka systems, basically the consumer group. We try to block the consumer group. So Kafka will say, okay, this consumer is done. It's not responding because the consumer group has a heartbeat. So we try to, okay, it's not responding fast enough. Then I'll spawn a new consumer and try to do that. It's very dependent on the way you have implemented this. It's very dependent on whether you can do that or whether you have to. For example, in the case of enrichment, you cannot split it, and it's out of your control if you have to query an external system. So in that case, you have to try to do it with consumer groups. But in the case you could have any control over whether an operation can be split or can be, or you have more control about the timeouts, you could start tweaking Kafka. There are several parameters that you can use at the consumer level or at the producer level to try to match it to your configuration. It's not easy, and it's very dependent on what you're trying to do, but it's a way to explore. The next question. Thanks very much for your interesting talk. Does Kafka use any hardware acceleration for the processing of the analytics? Well, it all depends on what you mean by that. Kafka by itself doesn't require any hardware acceleration. Your system, if your system has, for example, to perform statistics or crypto operations and you have hardware on the outside, you can implement it yourself. But Kafka as such does not require any hardware acceleration. The next question: what are the closest alternatives to Kafka in open source, commercial, and cloud solutions? Well, this is a tricky question because none of the other alternatives work in a similar way. So one similar system, or at least in the terms of the streaming, is RabbitMQ. People seem to be very happy with RabbitMQ, but RabbitMQ, it's a different system. It doesn't work the same way as Kafka. Another system that people have started using for this is SQS in AWS. I don't know what's the name of the Azure alternative or the Google Cloud alternative, but they all have their own queuing systems. However, with a big note of caution, there are some problems with using SQS and these queuing systems, because if you build a big enough backlog, then you're going to have problems fetching messages. All these queuing systems work by hiding messages while you're processing them. So if you have a very large backlog, you might not be able to process all of them, and you will have to start tweaking them. But so far, the only one that I know that provides the same level of performance is RabbitMQ. But I haven't used it myself, so I don't know exactly how it works. Any other questions? No, then I thank you for your time. I hope you enjoyed the presentation.